Last time, we were just starting out in section 8.2. Section 8.2 is on series. Now, we finished up 8.1, which is on sequences, and also, if you go over here to your Canvas site, you should be recognizing this fine fact. We're back into the flow of things again. So over to our Canvas site, when I go check on assignments and stuff, the pre-section quiz for section 8.2 was due 15 minutes ago. It was due at 11 o'clock. So we're back on schedule. 8.2, but I actually tried to get you guys to do 8.2 before because we started 8.2 last time, but I hope to get the majority of 8.2 done today. So 8.2 is on series. And what exactly series are is the summing of a sequence. And we're going to try to figure out when these guys converge and diverge. That's what chapters 8.2, 8.3, and 8.4 literally are about. An infinite series that we're adding up a sequence here, and we're trying to figure out if these things are going to converge to a particular number, add up to a particular number, or are they going to diverge. Now, you look at this thing and go, well, how can this relate to calculus? The fact of the matter is that, Riemann sums, how we invented the integral, actually came from that summation. So you're going to see some nice comparison between these two things. So it is very important for you guys to actually pay attention to this. Also, we don't just torture you guys with this stuff because we think it's fun to watch you guys squirm as we introduce new material with you guys. This stuff is actually very important. Depending on what your major is, you're going to see this stuff again and again and again. And my electrical engineers especially, the concept of signals, you're going to be in a wonderful world of series. When you get into differential equations, we're going to be talking about Fourier series. We're going to be talking about several different other aspects of series. And these are going to be more towards your junior and senior year. But they're going to expect you to know the basic concepts of series, and that's what you learn in this class, is the basic stuff, and you're going to expand on that in differential equations and your higher level courses. So this material is very important to you guys. So last time we did the pre-section video. Please watch the video and take the notes off of the problems I did there. Last time we were just doing some algebra review of exponential functions and how they basically work and some of your properties of exponents. So I want to pick it up right here with the definition and actually working on the concept of series. You know a sequence. A sequence is nothing but a listing of numbers. A1, A2, A3, all the way out to A5, and keep on going. This is an infinite sequence. A corresponding series is going to look like this. So pay attention to your terminology and notation. The sum as n goes from 1 to infinity of an. And what that's equal to is a1 plus a2 plus a3 plus a4 plus a5. And it's going to infinity, so plus ... and goes on forever. This is an infinite series. This is an infinite sequence. So we introduce you guys, chapter 8.1, the concept of a sequence, a listing of a number, so we can introduce section 8.2. We're going to add these guys together. So, write out. Here's a sequence right here. And then write out the sequence, and then write out the series and tell whether they're going to converge or diverge. So my formula for AN for a sequence is 3 times 1 over 10 to the n. To write out a sequence, with a sequence you always start with n equals 1. So we're going to write this guy out. N equals 1, n equals 2, n equals 3, n equals 4, ... See if we can catch a pattern here. This is a sequence, so they're going to be separated by commas. So plug in n equals 1. 1 divided by 10 to the first is 1/10 times 3 is 3/10. Plug in equals 2. 1/10 squared is 1/100 times 3 is 3 over 100. Catch a pattern here. N equals 3. 1/10 raised to the third power, 1/10 cubed is 1/1000th times 3 is 3/1000ths. And 10 to the 4th, 1/10 to the 4th is 1 over 10,000. Times 3 is 3 over 10,000, comma, ... This is the sequence. But you can see the pattern on this guy, but maybe it would be better if we just wrote it in decimal form. Maybe you can see the pattern. It's the same thing, but in a little different way. This would be 0.3 3 100ths is 0.03, 3 1,000ths is 0.003, 3 10,000ths is 0.0003, and dot, dot, dot. Now we're talking about a series. A series is the summing up of a sequence. This would be the sum, as n goes from 1 to infinity, of 3 times 1/10 to the n power. This would be 0.3 plus 0.03 plus 0.003 plus 0.0003 plus dot, dot, dot. So for a lot of people, series is very difficult for them to get their heads around. Because, number one, we're talking about a sequence. That's a listing of the numbers. And we can see by limits if this thing is going to converge or diverge. A series is the adding up of a sequence. How in the world can I add up an infinite number of things and actually be adding up to a particular number? But here's a great example of that so you can see this in its entirety. What is 0.3 plus 0.03 plus 0.003 plus 0.003? When you add it together, what do you get? You've seen this before. It's 0.3333333 dot, dot, dot. Keeps on going with that infinite aspect of it. And what's 0.3 repeating also known as? 1/3. So the series converges, when you get a number, it converges to 1/3. Now let's talk about comparing the series to the sequence. The other question was, talk about the sequence. The sequence, and I'll put him over here in a little box, was this AN is equal to 3 times 1/10 to the n. How do you tell if a sequence converges or diverges? That's what chapter 8.1 was all about. You do one thing. You take the limit as n approaches infinity. So the limit as n approaches infinity of 3 times 1/10 to the n. This would be 3 times, first rule of limits is plugging the number 1/10 to the infinity. We talked about this before too. What is 1/10 to the infinity? That's 1/10 times 1/10 times 1/10 times 1/10 times 1/10 dot, dot, dot. What's a tenth of a tenth of a tenth of a tenth? What do you got eventually? 0. Why? Because when your base is a fraction between 0 and 1, when you raise a fraction to an infinity, you get a fraction of a fraction of a fraction. It always goes to 0. If your base becomes bigger than 1, a number bigger than 1 raised to the infinity will blow up to infinity. Because this base is a fraction, you're going to get 0. Times 3 is still 0. So, the sequence converges to 0. The series converges to 1/3 when you add them up. They don't go to the same thing. And it's something big time different. You actually had to catch a pattern on these guys. Okay? So, what we do here to understand this process of trying to analyze a series from a sequence perspective is we talk about the concept of a partial sum. The partial sums is this. We started to give these little sums with a little subscript here. The big sum, which is going to infinity, we'll write as S. So S1 would be adding up just the first guy. That would be A1. S2 would be adding up the first two guys. That would be sum as n goes from 1 to 2 of AN, or A1 plus A2. S3 would be adding up the first three guys, A1 plus A2 plus A3. SK would be adding up the first K guys. A1 plus A2 plus A3 plus A4 plus A, da, 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 all the way up to plus AK, and you stop. And so once you look at this, you basically take the limit as K approaches infinity as you add on more and more terms, and that gives you your infinite series. So that's another way you can analyze a series by looking at its partial sums, and as these guys, you keep adding more and more terms on, you're trying to catch a pattern. So in this example, if I gave you down here, for the sequence 3 times 1/10 to the n, we want to find S1. S1 would be the sum as n goes from 1 to 1 of 3 times 1/10 to the first, or to the n, but you basically just plug in 1. You start at the bottom and you stop at the top, but they're the same, 1 and 1. So this will be just 3 times 1/10 to the first, which is 3/10. Or better yet for you decimal fans, 0.3. What would S2 be? That would be the sum as n goes from 1 to 2. You stop at 2 of 3 times 1/10 to the n. So you start, plug in 1 first. This will be 3/10 plus, then you plug in 2. 1/10 squared is 1/100, so it'll be 3 times 100, which is 3 over 100. That would be 0.3 plus 0.03, which would be 0.33. S3 would be the sum, as n goes from 1 to 3, of 3 times 1/10 to the n. That would be plug in 1, that's 3/10, plus plug in 2, that's 3/100, plus plug in 3, 1/10 cube's 1,000, so that's 3 over 1,000. And when you add that up, you get 0.333. And again, the key is to catch a pattern, because they're asking you for this one. What would SK be? Dot, dot, dot down here. Your SK would be the sum as n goes from 1 to k. So it's not an infinite series, it's finite. You're going to stop at k of 3 times 1/10 to the n. This would be 3/10 plus 3/100 plus 3/1000 plus dot, 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 plus 3 times 1/10 to the k. And you stop at k, plugging in k into this guy. But what would you get if you did this? Catch a pattern. S1, I got 0.3. S2, I got 0.33. S3, I got 0.333. What do you think SK is going to be? Catch a pattern. 0.3333, dot, dot, dot. 3, it does stop, but how many 3's do you have? K of them. You begin to catch patterns on this stuff. So, and from this, SK, you can make K go to infinity and actually get the infinite series. So these partial sums are derived to help you kind of mark through the first couple, but you cut it off because, you know, the idea of adding up an infinite number of stuff. But again, you're supposed to be catching patterns on this. Now, one of the most important series that you should have discussed in high school or junior high school or sometime thereabouts is something called a geometric series. So listen up and listen good, because I'm going to explain it to you in no uncertain terms. Series are difficult, but there are exactly 2 series. There are 2 series. We know exactly what they add up to be without much effort. Those 2 series are called geometric series and something called a telescoping series. And I'll get to the telescoping series later. This is the geometric series. A geometric series is a series where you go from one term to the next term and you're adding it up, but you multiply the first term by a particular constant to get to the second term. You multiply it by the same constant to get to the third term. You multiply by that same constant to get to the fourth term, dot, dot, dot. When you multiply a particular number times the first term to get to the second term, and that same number from the second term to the third term all the way down the line, that is called a geometric series. A geometric series has a formula, and the formula is this. The sum as n goes from 1 to infinity of a r to the n minus 1. A is your constant out front. It's just a constant. R is your ratio, and it's the r that's being raised to the n minus 1 power. Now, we usually use this guy right here, but you could have rewritten this series instead of starting at 1. We always start at 1 because, remember, a series is the summing of a sequence, and you start with the first term of the sequence. That's why 1. But if you want to make it look a little better in terms of the way the equation or the series looks, you can start it at 0. It's the same formula. It's the sum as n goes from 0 to infinity of a r to the n. The formula looks a little better, but this is really the way we kind of focus on it because it's the summing of a sequence. So we're going to actually use both at the end of the day. Right at the beginning, I'm going to use this guy. Towards chapter 8.5, I'll switch it over to this guy because you're going to see this mess again. But here's the deal on a geometric series. Once you've identified a geometric series, and that r is the number you actually, the ratio that you multiply the first term by to get to the second term. It's the same r you multiply by the second to get to the third term, so forth and so on. And here's the deal. I told you, in a geometric series, we know exactly what the series adds up to be. It converges to, it adds up to be, converges to the formula a over 1 minus r, provided if the absolute value of that ratio r is less than 1. And the series is going to diverge. Diverge means it's going to either add up to infinity or add up to negative infinity, depending on the sign of it, if the absolute value of r is greater than or equal to 1. So that ratio, if the ratio is a fraction that's less than 1, absolute value speaking, then the series is going to converge, and we know exactly what it adds up to be, the formula a over 1 minus r. If that r happens to be greater than or equal to 1, the series is going to diverge. So that's going to be our question. We're going to give you a geometric series and ask you if it converges or diverges. If it converges, what does it add up to be? Yeah?
So the ratio is just the value in which it's changing by every time.
What it's the value that it's changing by every time. And that's a great way of looking at it because of interesting web work sometimes doesn't write it in formula version. They sometimes write it out in terms, and you can figure it out by what did I do to the first term to get to the second term. That's going to be your R value. So now, this one's slightly different because I'm starting n equals 1 here, but it's a similar problem as what we did before. Now look at the directions. It says, determine whether the each series it will converge or diverge. If it converges to what? I mean by converging in series means what is it going to add up to be? So it's a different kind of converging. Converging in sequences is what is the limiting value. Convergent in series is what is it going to add up to be. So in this one, the goal is to get you guys in formulas. Now, here's the deal. A geometric series, get this in your notes because you're going to have to recognize this stuff. This is your first of 100 definitions from this chapter. A geometric series is the sum of a number raised to a power of n. It's a number raised to a power of n, maybe times a constant, but that's it. It's only a number raised to powers of n. That's what makes geometric series. So in this problem here, this is my formula. The sum as n goes from 1 to infinity of 3 times 1/10 to the n minus 1. If you analyze it from this sum as n goes from 1 to infinity of a r to the n minus 1, you're supposed to recognize that my sum matches up completely. A is equal to 3 and r is equal to 1/10. Does that make sense? So, and we check it by our little formula, the absolute value of r, the absolute value of 1/10 is 1/10, which is less than 1. Being less than 1 tells me this thing is going to converge to the formula a over 1 minus r. Now I plug in my information into this guy. So this thing is going to converge to a is 3, over 1 minus r is 1/10. Let's do some basic math. What is 1 minus 1/10? 9/10. So this is 3 divided by 9/10. And when you divide by a fraction to clean it up, you invert and multiply by the reciprocal. This would be 3 times 10 over 9. 3 goes into 9 3 times. This is 10 over 3. So it converges to 10 over 3, but 10 over 3 is the same thing as 3 1/3, if you think about it. Or for you decimal fans out there, 3.33333. Okay? So because it's very similar to what we did before, but we had that one extra term. And I wanted to show you guys this. If you wrote it out, sum as n goes from 1 to infinity of 3 times 1/10 to the n minus 1, you plug in 1. N equals 1. And here's the deal. When you plug in 1, 1 minus 1 is 0. 1/10 to the 0 power is 1. Times 3 is 3. That's where that 3 showed up at. Then plus, when you plug in equals 2. 2 minus 1 is 1. 1/10 to the first is 1/10 times 3 is your 0.3. Then you plug in n equals 3. 3 minus 1 is 2. 1/10 squared is 1/100. 3 divided by 100 is 300ths or 0.03 plus ... And when you put it together, you see that 3.33333 stuff, which gives me my answer. But I didn't have to write it all out and catch a pattern off of it. All I had to do, because I recognize it as a geometric series, is put it into the geometric series formula. But that's where the thing is going to get kind of interesting for you guys, because you know we're going to mess up these formulas and make you do algebra on these series. So take a look at the next guy. Listen to my words. The question is the same. Here is a series. Does it converge or diverge? And if it converges, what does it converge to? What does it add up to be? Remember, this is a series, so when we're talking about converging, we're trying to figure out what it adds up to be. Now, what do you recognize in this problem? It's the sum as n goes from 1 to infinity of 4 times -1 to the n plus 1 times 3/4 to the n plus 1. The first thing you should recognize is it's a geometric series. How do you recognize that? It's a series, big old sum in front of it, with numbers being raised to powers of n. Two different numbers, a -1 to the n plus 1 and 3/4 to the n plus 1. So the first thing I'm going to do is I'm going to use my property of exponents. Because these guys have the same power, I can factor out that power. So this would be equal to the sum as n goes from 1 to infinity of 4 times -1 times 3/4, pulling that out and factoring out the power, n plus 1. Remember, my ultimate goal on a geometric series is to write it as the sum as n goes from 1 to infinity of a r to the n minus 1. That's what I'm trying to make it look like, so I can pull off the a and pull off the r, and then analyze it. Classic engineering calculus, analyzing in a particular format. So, this is equal to, combining my terms, sum as n goes from 1 to infinity of 4 times -3/4 to the n plus 1. Well, I got my sum working out. Sum as n goes from 1 to infinity, so we're good to go there. I got 4, good, got a constant there. My r is -3/4, but it's raised to the n plus 1. What power do I actually want in terms of a geometric series formula? I don't want n plus 1, what do I want? N minus 1. Listen to my words. I don't want an n plus 1, I want an n minus 1. I've got too many. How many too many do I have? I want an n minus 1 power, I've got an n plus 1. So I'm going to pull off some of them. How many am I going to pull off? 2. So this would be equal to the sum as n goes from 1 to infinity of 4 times -3/4 to the squared times -3/4 to the n minus 1. And I want to prove the mathematics to you guys. When you multiply like bases, what do you do with the exponents? Think about the preview chapter here. When you multiply by bases, you add their exponents. Okay, think back 4th grade. It's great. Okay, when you multiply bases, you add their exponents. What is 2 plus n minus 1? N plus 1. It's the same thing, but I pulled off what I didn't need because I needed n minus 1 power according to my formula. So this -3/4 squared is going to be pulled into the constant. So this is the sum as n goes from 1 to infinity of 4 times -3 squared is 9, 4 squared is 16, times -3/4 times n minus 1. And one more cleanup. It's all about the algebra. The sum as n goes from 1 to infinity of. Now 4 goes into 16 4 times, so you actually get 9/4 times -3/4 to the n minus 1. Now from this, now I've got it written in geometric series formula. I can tell you that A is actually equal to 9/4, and the R is equal to -3/4. And since the absolute value of R, absolute value of -3/4 is 3/4, which is less than 1. So according to my form, when the absolute value of R is less than 1, we know this is going to converge or add up to the formula A over 1 minus R, which is 9/4 over 1 minus -3/4. And you can clean that up if you want to. I'm going to sit there and use my calculator on this thing just for time's sake and just to show you how to do it. But remember, when you do it on the calculator, parentheses around your numerator, 9 divided by 4, divided by parentheses around your denominator. 1 minus parentheses -3/4, close parentheses for the fraction, close parentheses for the denominator. So I'm trying to make sure one careless error kills this stuff. Parentheses around the numerator, parentheses around the denominator, and I'm making it look exactly the way it looks, and I end up getting 1.278, whatever. I can convert that to a fraction, and you get it's equal to 9/7. So this series, when it adds up, is going to add up to, converges to, from a series perspective, of 9/7. Does that make sense? So, how bad can they make them? Wait, let me show you. Turn page. Take a look at this next guy. It's the sum as n goes from 1 to infinity of 2 raised to the 2n times 3 raised to the 1 minus n. Well, the first thing you got to know is what kind of series is this guy? Well, one, we only have one series down. Don't worry, we'll add to this list later. But I can tell you it's a geometric series because look at the series. It's a sum and that's nothing but numbers raised to some kind of power of n. I've got 2 raised to the 2n times 3 raised to the 1 minus n. Now, remember, on a geometric series, what we're looking for. So my target is to make it look like the sum as n goes from 1 to infinity of a times r to the n minus 1. So, and remember, this is going to converge to a over 1 minus r if the absolute value of r is less than 1, and it's going to diverge if the absolute value of r is greater than or equal to 1. So that's my formula. I have it memorized. So, I want a power of n minus 1. First thing, double check. The summations start out in the right spot. So it's the correct sum. Sum as n goes from 1 to infinity. So my sum's good. But I want to have a power on my r of n minus 1. Well, I'm going to have to worry about that 2 to the 2n in just a second. But look at the 3. What's the power on the 3? It's 1 minus n. It's backwards. So to switch it around, what's the deal? Well, let me show you. This would be equal to the sum as n goes from 1 to infinity of 2 to the 2n times 3 to the negative, I'm just cleaning this up, n minus 1. What is negative parenthesis n minus 1? You distribute the negative. That gives you negative n plus 1. And negative n plus 1 is the same thing as 1 minus n. And the reason why I wrote it like this is where the negative exponents get to go. I'm working exponential properties here. Where do you get to put negative exponents? To the denominator. So that 3 to the 1 minus n will turn into the sum as n goes from 1 to infinity of 2 to the 2n divided by 3. Negative exponent goes on the bottom, becomes positive. Raised to the 3 to the n minus 1. So that 3 to the 1 minus n actually turns into a 3 to the n minus 1 in the denominator. Now I got to focus on my numerator. Remember your exponential properties. We're going to beat them to death. When you have exponential properties, a power raised to another power, what do you do with the powers? Power to a power, multiply. But remember, you can work this stuff backwards. A power to a power, you multiply. So if you're multiplying exponents, 2 to the 2n, you can break that back as a power to a power. So this is equal to the sum as n goes from 1 to infinity of 2 squared to the n. Power to a power, you multiply, over 3n minus 1. Now, what exactly is 2 squared? It's just a number. What's that? 4. So this is the sum as n goes from 1 to infinity of 4 to the n over 3 to the n minus 1. But according to the geometric series, what form of the exponent do I want to have on any kind of number? I want to be raised to the n minus 1. Now, my denominator is good to go, 3 to the n minus 1. But look at your numerator. It's 4 to the n. I want a 4 to the n minus 1. I got too many. How many too many do I have? 1. So I'm going to pull off one of these guys. So this is the sum as n goes from 1 to infinity of 4 times 4 to the n minus 1. This exponent game that I'm playing here is the key to geometric series, divided by 3 to the n minus 1. And then now notice that you got two terms that have the power of n minus 1. You can factor out that n minus 1 power, and you're left with the sum as n goes from 1 to infinity of 4 times 4/3 to the n minus 1. So all this work is to get it into the form of the sum as n goes from 1 to infinity of a times r to the n minus 1. So now, based upon the format, what's a equal to? What's a? 4, the constant. And what is your r, your ratio being raised to the n minus 1? What is that? 4/3. The absolute value of 4/3 is 4/3. But what is 4/3? Compared to 1. 4/3 is what? Greater than 1. Being greater than 1, what's my answer? Therefore, the series diverges. And what I mean by diverges means it's going to add up to infinity. It's going to blow up on you. Does that make sense? It's not going to converge and add up to a particular number. It's going to add up to infinity. Does that make sense? Question? Yeah.
Where did that other 4 come from? To the 4 times 4 to the n minus 1. Where did that first 4 come from?
This one right here? Okay.
Where did that come from?
Where did this guy come from?
Yeah.
Okay. Originally, when you had this, I pulled off the 2 to the 2n, made it 2n to the 2 squared to the n, power to a power multiply, right? 2 squared is 4, so that's 4 to the n. But you want a power of n minus 1. So I've got one too many n's up here. I got one too many 4s, excuse me, because I want an n minus 1. So I pulled off one of them. There's a 4, and when you pull off one of them, you're still left with 4 to the n minus 1. Because remember, when you multiply, you add exponents. It's officially 4 to the first. 1 plus n minus 1 is actually the n. I pulled off what I don't need to get that n minus 1 power, and that became part of my a. Now, the next problem is you're getting the property of these exponent deals, playing with the exponents, turning them into a r to the n minus 1. But what if the sum doesn't start at 1? Look at this guy here. I got the sum as n goes from 3 to infinity of negative 2 times 1/3 to the n plus 1. First things first, to turn it into your geometric series formula, remember it's the sum as n goes from 1 to infinity of a r to the n minus 1. This is the look that I'm going for. I've got to start my summation. It's got to start at 1. What are we starting at? 3. Here's the rule on summations. To maintain equality, whatever I do to the summation, I've got to do the opposite to the n within the formula, in terms of the sequence. Whatever I do to the summation, I got to do the opposite to maintain equality to the sequence part of your series. So when I talk about a series, the series is the sum. What you're summing, this little an part over here, this is the sequence part of the series. Whatever you do to the summation, you're going to do the opposite to every n, wherever the n's are located at in the sequence part of your series. So here's the deal. I want to start this thing at 1. I'm starting at 3. How do I go from 3 and get it back down to a 1? What do I have to do? I got to take away 2, right? So I'm going to take away 2 from the n's here. So what I'm going to have to do to my problem is, wherever there's an n, I'm going to have to add 2 to the n's. There's only one n here, to maintain balance. Whatever I do to the summation, I do the opposite to the n's in the formula. So this would be equal to the sum as n goes from 1 to infinity. 3 minus 2 is n, 1 to infinity, of negative 2 times 1/3 to the n. We added 2, n plus 2, and plus the plus 1 was already there. This was the new part we added. So help me out here. What is n plus 2 plus 1? How much you got? N plus 3. Sum as n goes from 1 to infinity of negative 2 times 1/3 to the n plus 3. So now my summation is a big old check. It's working. The sum as n goes from 1 to infinity. Now I got to focus back on my sequence part. What power do I want on my r? I want an n minus 1 power. That's what the formula says. But what power do I have? I've got n plus 3. I got too many again. My question to you guys is this. How many too many do I have? How many do I need to pull off? I've got n plus 3. I want an n minus 1. How many do I need to pull off? 4. So I'm going to pull off 4 of these 1/3. So this will be the sum as n goes from 1 to infinity of negative 2 times 1/3 to the 4th, and that makes it 1/3 to the n minus 1. And you can always double check yourself, because when you multiply like basis, you add exponents. 4 plus n minus 1 is n plus 3. Now, what is 1/3 to the 4th power? Well, when you got powers, strict multiplication division, you can distribute. 1 to the 4th is 1. 3 to the 4th is 81. 3 times 3 times 3 times 3 is 81. So this gives you the sum as n goes from 1 to infinity of negative 2 over 81 times 1/3 to the n minus 1. I just combined these two guys together, the negative 2 times 1/3 to the 4th, to get a constant. And now you will recognize that this constant is my A. A is going to be equal to negative 2 over 81. Your R, your ratio, is 1/3. That's what's being raised to the n minus 1 power. The absolute value of R, absolute value of 1/3 is 1/3, which happens to be less than 1. being less than 1, and the geometric series, we know that this series is going to converge to, is going to add up to the formula A over 1 minus R. A is negative 2 over 81 divided by 1 minus R, which is 1/3. And again, I'm going to put this on the old calculator here so you guys can see this. Parentheses around my numerator. Negative 2 divided by 81 divided by parentheses around the denominator, 1 minus 1/3. And I get negative 0.037037. But of course, you know those repeating decimal means it's a nice fraction. The answer is negative 1 over 27. This series converges to negative 1 over 27. So I want you to notice also in this problem that not only does it converge, you can converges to a negative number. You can add up stuff to make it up to a negative number, just like you can add up stuff to make it to a positive number. You can add up stuff to get infinity. You can add up stuff to get negative infinity. But infinity and negative infinity in terms of a series is called divergent. Anything else, when you get a number, is going to be called convergent, but you're trying to figure out what it's going to add up to. The next type of series is called telescoping series. Now, a telescoping series is a technique used when summing up a sequence that is the form of, listen up, it's a special case here. A telescoping series is the form of a fraction, usually a fraction minus a fraction, where the numerator and it's a fraction minus a fraction, where the numerators are the same, but the denominators are going to be slightly different by a constant, n plus 3 versus n minus 2 or something like that. Usually it's going to be a fraction minus a fraction where the numerators are the same and the denominators are going to be slightly differing by a constant. Okay, so here's an example of one. The sum as n goes from 2, focus on it, 2 to infinity of 3 over n minus 1 minus 3 over n plus 1. This is a classic telescoping series. How do I know? It is in the form of a series, big old sum, of a fraction, rational expression, minus rational expression there, fraction minus a fraction where the numerators are the same. That's your key. The numerators are going to be the same. And it's real simple to figure out what it's going to add up to. And then once you had to figure it out, all you got to do is write out a bunch of terms. Now the trick is how many you're going to need to write out. And I'm going to show you a trick on doing that too. But I'm just going to write out some terms. So this will be equal to, what is this series going to start with? What number? Very important. What number does it start with, this series? 2. You start with n equals 2, then n equals 3, then n equals 4, then n equals 5, then n equals 6, ... That should be good enough. Write them out. Plug it in. And don't clean it up. Just write it out. N equals 2. Plug it in. This will be 3 over 2 minus 1 is 1, minus 3 over 2 plus 1 is 3. When I plug in equals 2, I get the 3 over 1 minus 3 over 3. Then it's a series, so you're going to add that 2. Plug in equals 3. That'll be 3 over 3 minus 1 is 2, minus 3 over 3 plus 1 is 4. Plus, now plug in equals 4. That'll be 3 over 4 minus 1 is 3, minus 3 over 4 plus 1 is 5, plus plug in equals 5. 3 over 5 minus 1 is 4, 3/4, minus 3 over 6. Probably you can catch a pattern, that's always the goal in life, off this guy. So if you look at the next guy, you probably figure out the pattern. The next one's going to be what? 3/5 minus 3/7, but let me just prove it to you. Plug in 6. 6 minus 1 is 5, so that's 3/5. Minus 3 over 6 plus 1 is 7. There you go. Plus ... Now, these series were analyzed during the 16 and 1700s, 17th century stuff, mathematics. Now, to understand mathematics, don't think too deep in how we come up with names for stuff, because we have to explain it to other people. Think, first off, 17th century, and think of the word telescope. Think about what a telescope looked like in the 1700s. What does a telescope look like in 1700s? You know, you've seen Pirates of the Caribbean or stuff like that. What did the telescopes look like? All right, so I see this motion of hands. I'm doing this. It looked like basically a can was inside of, a can was inside of, so you would extend it out and compress it back. So the pirates didn't walk around with this thing about 14 feet long or anything like that. This thing was about, 3 or 4 feet long, and there was a cylinder inside of a cylinder inside, so you could collapse it down and they could extend it back out. 17th century telescope. Collapsing it back down. You've extended it. Watch the collapsing back down. 3 over 1 minus 3 over 3 plus 3 over 2 minus 3 over 4 plus 3 over 3 minus 3/5. 3 over 3, that's a minus 3 over 3 plus 3 over 3. They're going to cancel. Now look at your next term. Plus 3 over 2 minus 3 over 4. This is plus 3 over 4. The minus 3 over 4 plus the 3 over 4 cancels. You with me? Look at your next term. I've got plus 3 over 3, which already canceled, minus 3 over 5. I got minus 3 over 5, and I got minus 3 over 6 plus 3 over 5 minus 3 over 7. This minus 3 over 5 and this plus 3 over 5 cancels. And notice something or other. Here is your first block that completely cancels. Does that make sense? And once one block cancels, all the other blocks that follow are going to start canceling and collapsing down. Let me just show you. If I plug in n equals 7, n equals 7 into this thing would be 3 over 6 minus 3 over 8. The minus 3 over 6 and the plus 3 over 6 cancels. The next block cancels. And then the next block cancels. And the next block cancels. And all the rest of the block cancels. So once everybody starts canceling, what are you left with? There were 2 terms that didn't cancel on this example. 2 terms. What are they? 3 over 1 plus 3 over 2. This is 3 plus 3 halves, which is 1 1/2. The answer is 4.5, 4 halves, or for you big fraction fans, 9 halves. This is what it converges to, 4.5. It's the terms that were left over. Once a full block cancels, all the other blocks after that are going to cancel out. It collapses. So telescoping series, as long as it's a fraction minus a fraction where the numerators are the same, are always going to converge, and it converges when you start writing them out, the terms that were left over. Once a full block cancels, everybody behind him cancels. That collapsing idea of the telescope. Does that make sense? But now, how did I know how many terms to write out? That's always key. What is the difference? Now remember, the numerator is the same. What's the difference in the denominators? N minus 1 and n plus 1. How many terms different are they? N minus 1, n plus 1. 2 terms different, right? You can go from n minus 1 to n plus 1 by adding 2. So it's 2 terms. So if you look at it, all you needed was the first 2 terms. And those were the terms that I used. But if you want to figure out how many terms to write out to show your work, take the difference between your denominators, double it, and add 1. So this is there were 2, the n minus 1, n plus 1 was 2, difference of 2. Double that, what do you get? 4 plus 1 is 5. You had to write at least 5 terms before you see a block completely canceling. That's going to be the rule. Take the difference between the 2, double that so you can show the canceling, and add 1 more so you can show the block completely canceling. So 2 was my difference, times 2 is 4, plus 1 is 5. If I wrote out 5 terms, I can show you a block canceling, and then all the other blocks can cancel after that. Once one block cancels, all the other blocks cancel. Okay? Does that make sense? So your telescoping series always, but what's a telescoping series? It's a fraction minus a fraction where the numerators are the same. Take a look at this guy. It's the sum as n goes from 5 to infinity of 3 over n squared minus n minus 6. This is not a telescoping series, but it is. But it doesn't look like a telescoping series, Dr. Taylor. You're right, it does not. It's not a fraction minus a fraction where the numerators are the same. Great time to start reviewing for that old final exam. Look at it. It is 3 over n squared minus n minus 6. Did you not notice the denominator? You can factor it. N squared minus n minus 6 factors into what? N minus 3 times n plus 2. 3 on top. And to make it a fraction minus a fraction, do you remember the rules? It is called, that's right, it's coming back to haunt you, partial fractions, yay. Back to chapter 6.2, or 6.3 actually, 6.3, partial fractions. So this 3 over n minus 3 times n plus 2 is going to factor into n minus 3 denominator, n plus 2 denominator, and because these are degree 1s, the numerators have to be constants, degree 0s, a and b, we'll put a big old plus there, doing partial fraction techniques from what we did a month ago. Does that make sense? And now how do I do partial fractions? I'm going to multiply both sides by my common denominator of n minus 3 times n plus 2. This will give me 3 is equal to a times the n minus 3 is canceling out for the n plus 2. Plus b, here the n plus 2 is canceled, n minus 3. I got 2 letters to solve for. What is your suggestions on the n's that I should pick using the annihilator method? I'm going to pick negative 2 and positive 3. So 3 and negative 2. When I plug in 3, this 3 stays the same. 3 plus 2 is 5, so I get 5a. Plus b, 3 minus 3 is 0, it annihilated the b. And solving for a, dividing by 5, a equals 3/5. Now plug in negative 2. There's nothing on this side to plug into. You just get 3 equals a times negative 2 plus 2 is 0, plus b times negative 2 minus 3 is negative 5. That goes away. So 3 is equal to negative 5b, making b equal to negative 3/5. Notice you get the same number, but one's negative and one's positive. So when you back and substitute it back in here, this is going to be equal to the sum as n goes from 5, it doesn't change, to infinity of a, which is 3/5, over n minus 3, plus b, which is negative 3/5, over n plus 2. And now this problem, thanks to the help of our partial fraction techniques, has just turned into a fraction minus a fraction where the numerators are the same. It's a telescoping series. Telescoping series always converges, but the question is, you've got to figure out what it's going to converge to. Question for you. All right, this is a pain, but how many terms do I need to write out? What is the difference in your denominators? You notice numerators are the same. Plus a negative makes it minus. The sum as n goes from 5 to infinity of 3/5 n minus 3 minus 3/5 n plus 2. What is the difference in your denominators? How many? 5. Double it. 10. Add one more. You got to write 11 numbers. What? 11 numbers. What number are we starting out with this thing with? 5. N equals 5. N equals 6. N equals 7. N equals 8. N equals 9. N equals 10. N equals 11. N equals 12. 1, 2, 3, 4, 5, 6, 7, 8. N equals 13. N equals 14. N equals 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That should do it. And one more for good measure. N equals more. More is always better than less. This is how many terms I need to write out to show you the terms. And then after that, the dot, 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 you're going to see an entire block cancels. Once an entire block cancels, the numbers that are left over in the front are the numbers you're going to add up to be able to get your term. Do you see what it converts to? Does that make sense? We'll finish this problem next time. Study hard on this stuff, and I will see you guys. We'll finish up section 8.2 and then move on into section 8.3. There are 7 tests you're going to have to memorize as well as names of series. You've got 2 named series right now, geometric series and telescoping series.